Hi and welcome. This is our session number 10. By next time, so next session will be just an exercises solving session. Okay. By now we have enough things to talk about. Okay, and enough things to solve stuff about. Ideally, we should have went into partial derivatives, but I will leave this for later because it really needs a lot of discussion, especially the intuition for partial derivatives and the way it's formulated for non-vector spaces. Last time we were talking about just maps which are going, so session 10, okay. As a reminder, we are still in we're in chapter 2, okay, chapter 2 of Cartan, and specifically last time we were on pages 32 and 33, okay, so 32, 33, and specifically we were in section number 5, okay. Yes, so I was saying last time we were talking about the derivative of a map which is going from a non-vector space E, so let's say from an open subset U of E, into some F, where F happens to be a product of non-vector spaces itself. Okay. So the thing we cared about and wanted to discuss was that of the components of this function. Such a function. We can talk about components of such a function. So this function actually looks like this. So x is getting mapped to some in the product, okay, f1 of x up to fn of x. Last time I was saying k, I think. I was denoting this by k, does not matter much. Okay, so f1 of x, fk of x. These were the components which I was talking about when I was talking about the projections, the projection maps. So I remind you in a bit about the projection maps, but basically what I was understanding by the projection of the map f itself, okay, on the ith coordinate is just this mapping fi, which is over here. Each fi, which is a component function of f, okay, is the composition of f with the projection function. Okay, now what's good was that the projection function pi, each projection function, so I ranging between 1 and k, is actually linear continuous. Okay, and so is the injection ui you also talked about. So I will remind you about the pi and ui in a bit. I wanted to mention something which I think I didn't go much into last time, which is the intuition of what we're doing here. So basically the theorem which we were proving last time before the session ended, okay, was that if you have a function f, okay, from some u inside E into a product of non-vector spaces, okay, then, and so with a point, so let A belong to U, okay, then f is differentiable at A if and only if each of its component functions, okay, is differentiable at A. And this is what we usually saw in basic calculus when you have something like, especially in physics-related courses, or so when you have curves, let's say you have parametric curves. So gamma of t being equal to something cosine t, sine t, t squared, expressing some curve lying inside the space R3, okay, parameterized by some t lying inside some interval, okay, this is gamma, and we'd usually say, okay, this is the first component gamma 1, this is the second gamma 2, and this is the third gamma 3, okay, and then we'd say, okay, gamma, since each gamma I is differentiable, okay, so is gamma, and we'd say, well, gamma prime of t, well, you just differentiate each component. First component, okay, derivative is minus sine t, second, okay, cosine t, the third 2t. Okay, and that's literally what we were doing last time. Okay, that's secretly what we were doing last time. Let's say a function f is differentiable, okay, when it's going into a product of non-vector spaces, if and only if each component function of f is differentiable as well at a certain given point. Okay, at A, if only if this is correct. Okay, and we were saying furthermore in the remark following it, that the derivative of f at the point A is just the sum from I equal 1 to k of ui composed with dfi at A. And what does this sum mean? This sum over here, okay, which is equal to df of A. This is really what we would understand as the vector of derivatives inside the usual, let's say, Euclidean situations and stuff like that. Okay, why? Because the UI function, so here it's due to recall the UI and the PI. So recall, what was the UI doing? So we had some F1, F2 up to Fk, some given non-vector spaces, okay? And we were considering F, the product of the Fi's from I equal 1 up to K. We're saying, okay, the function UI, well, we defined first the projection, I guess. So the projection map, PI, for a given I between 1 and K, is the map which takes you from F into an individual Fi. So imagine you have these sets, okay, you're picking triplets from them, okay. What the projection is doing is that, okay, you're picking a triplet XYZ. The projection is taking you inside one of these spaces. So the projection on the second coordinate will take you inside this space over here, okay, and it would return Y for this XYZ. Okay, that's what the projection is doing. It's literally projection in the way you understand it. Okay, so we define PI, okay, from F into Fi to be the map given by, well, PI of a certain X belonging to F. So say X belongs to F, X is equal to some X1 up to Xk. Okay, so PI of X is just Xi. You are projecting on the ith coordinate. Okay, and that's it. Okay, now what was the UI? Well, the UI is sort of trying to do something that completes, say, or let's say acts in an inverse manner to the PI. Instead of projecting, it's actually trying to do something, the inverse of this operation. So the PI is taking you from this product of spaces into one of the spaces, while the UI is taking you from one of the spaces into the product of the spaces. Okay, and what the UI is doing, so UI is going from some Fi, going from the Fi to F, which is the product of the Fj's, j equal 1 to k, and what the UI is doing is that it's taking some let's call it just x for now, okay? I'm using x for a vector, so let's just call it alpha. Okay, UI of alpha, okay, this thing is just the vector consisting of zeros everywhere except at the ith component, okay, where it has an alpha, the thing which is its argument. So it's trying to inject it's an injection basically. It's trying to inject the individual element which is inside the Fi into the product space. Okay, and it's sort of an inverse of the PI. It's not an inverse because the PI is not bijective and the UI is not bijective. Okay, now what's special about them is that the PI is surjective. Okay, that's clear. Okay, if you are and I think I talked about this last time. Okay, PI is surjective and UI is injective, and both of these are very easy to prove. Okay, and UI is sort of it's not sort of, it's literally a right inverse for the PI. Okay, right in the sense of on the right, lying on the right. So we talked about this, that the fact that the PI around UI is the identity map of Fi. And why is this the case? Because, well, if you're taking the UI, which is going from Fi into F, and then you are going, so let me put the UI under the arrow. So this is the UI here. It's taking you from Fi to F, and then the projection, okay, is taking you from F to Fi again. Okay, what's happening? So you're taking some xi, okay, and you are mapping it into the vector which has zeros everywhere except at the ith position where it has an xi. And the PI is once again projecting this vector onto the Fi space, and this means that it picks out the element xi. So it's returning xi again. So literally, the UI is what we call a right inverse of PI. It's an inverse of PI, but to the right. Okay, PI does not have an inverse to the left. Okay, and PI does not have an inverse to the left, and UI does not have an inverse to the right. Okay. Just to be clear, this concept of a left or right inverse is coming from ring theory. Okay, if you have seen some ring theory, you would know if you have a certain ring with the plus and dot, the binary operation which makes it into a group, and the dot which makes it into a ring, then generally speaking, an element x of R, okay, although it has an inverse with respect to addition, does not necessarily have an inverse with respect to multiplication. So it's not generally true that there exists a y such that x dot y is equal to 1 and y dot x is equal to 1. Okay, but furthermore, of course, when a certain element of a ring, so let's say x, okay, has a right inverse, say y1, and has a left inverse, say y2, okay, then y2 is the same as y1, okay, and then x is just invertible, okay. But generally speaking, an element x of a ring R, okay, might have a left inverse, so there might left inverse, so there might exist a y such that so might have a right inverse, okay, so it must they might exist a y such that x y is equal to 1, okay, and we call y a right inverse because it's coming on the right of x, okay, but it might also or let's say, okay, there might be a right inverse, but there needn't be, okay, but there needn't be also a left inverse, okay. So it might be that there exists no z such that z dot x is equal to 1. That's where the concept of right and left inverse is coming from, okay. I thought it would be good to make this a bit clear, because it might be confusing a bit to say what means for a map to have a right inverse and left inverse. You can also understand it purely in terms of maps. You do not need ring theory for this, okay, but this is where the terminology is coming from. So back to our discussion, and maybe just as a brief remark, so a remark which is general from set theory, okay, if f is a map, okay, such that f has a right inverse, okay, then f is necessarily surjective, okay. So what's the proof of this? So suppose that there exists some g which such that f times g is equal to identity, f round the g in the sense of composition is equal to the identity, so it has a right inverse, okay, and so let's say f is going from x to y, okay, so let y belong to y, okay, and consider and say just look at f of g of y being equal to y, okay. So because f around the g is equal to the identity, okay, then, well, f around the g of any element y of y, of course g is going from y to x, okay, is equal to y itself, okay. So then f of g of y is equal to y, and then, well, there exists, so this means so there exists an x in x such that f of x is equal to y, okay, and x is just g of y. By a similar reasoning, okay, if f, so remark as well, if f has a left inverse, okay, I shouldn't say by similar reasoning, what I mean is by like a similarly easy way, okay, if f has a left inverse, then f is necessarily injective, okay. And why is this the case? Well, proof. Suppose that there exists a g, okay, going from y into x, so f is going from x to y, okay, such that g round f is equal to the identity, okay, then given some x1 and x2 in x, okay, if f of x1 equals f of x2, then g of f of x1 equals g of f of x2. Not doing anything specially, just applying the map g both sides. Okay, so then, well, g round f is the identity, so I get x1 equal to x2. That means it's injective, okay. So that's another way to see why the pi, okay, is so remember that pi round ui is just the identity of fi, right? And this means that pi has a right inverse, and this implies by above that pi is surjective. Okay, so that's one formal way to see that pi is surjective. And ui has a left inverse, namely pi. Okay, so ui is injected as well. Okay, enough with this. Now let me now very briefly just remind you of these two important facts. So the first fact, the pi for each I, okay, is linear and continuous. Okay, and that's something I mentioned last time. Linearity, I don't think I did it, but it's very trivial. And continuity, I mentioned why. Okay, the ui is also, for each I, okay, is also linear and continuous. And the reason, okay, for the ui, I didn't mention, I think, last time. So similarly, of course, the ui is going from fi into the product f, okay, product of the fj's. And the way ui is working is taking some xi into 0, 0, xi, 0, 0. Yeah, xi at the ith component. So if you're looking at the norm of ui of xi, okay, inside the product, this thing, okay, if you're taking the let's say the max norm, we already talked about how the max norm is the same as the two norms, the same as one norm. So let's say you're dealing with the max norm, so the max norm of ui of xi, okay. Well, this is just the maximum between the components of ui of xi. So the maximum between. So let me rewrite this. So okay, this is the norm of 0, 0, xi, 0, 0. Okay, max norm. So this is what? This is by definition the maximum. Okay, of what? Of 0. Okay, the first component. 0, possibly the second component. Okay, and so on. And at some point you will have absolute xi, or I should say norm xi in fi. Okay, and then all the way, zeros all the way, okay? And then this is just norm xi in fi, right? I mean, this is the, all the others are zeros. Okay, and this means that actually the norm of ui of xi will be equal to the norm of xi, and that's true for all I, for all, I should say xi, okay? For all xi in fi. So this means that the norm of ui is actually equal to 1. It's not just that it's less than or equal to 1. We can actually say the norm of ui is equal to 1. The operator norm, okay, operator norm of ui. And that's why ui is continuous, okay, continuous, bounded linear map. Why it's linear is also very easy, okay. I assumed anyway that it's linear before finding its norm. Okay, and the importance of the ui being linear, there's many things. Among them, when we wanted to find the derivative, so let's recall the f was going from e into the product of the fi's, or the product of the fj's. Okay, and we said that, okay, if for each j, fj is the jth component function of f, or i.e. if you want, for each j, fj is the projection round f, the jth projection round f. Okay, then, of course, assuming that f is differentiable, or that each fj is differentiable, which are equivalent to each other at a certain point a, okay, then the derivative of f at a can be expressed in terms of the derivatives of the fj's at a in this formula. The sum of uj composed with dfj at a, okay, from j equal 1 up to k. And I think at the beginning I talked about the intuitive meaning of this. Yeah, so I might have mentioned it briefly, so let me restate it. Okay, so the thing what's happening here, okay, I was trying to remind you of the uj for this purpose. So what's this kind of thing here? What's this kind of thing? So for j equal 1, let's say, we're looking at u1 composed with df1 at a. Okay, what's this? If you are taking a point h, applying this to a point h, okay, this is u1 of d1, df1 of a h, okay, and this thing, what does the u1 do? Well, it places this thing in the first coordinate. So this is df1 at a, h, 0, blah blah blah, zeros, okay. And then for a general, for j equal 2, the same story, okay. So uj, u2 composed with df2 at a applied to h, this thing is just 0 df2 at a h, and zeros all the way. And so, okay, if you are looking at the sum of the uj composed with d fj at a, j equal 1 up to k, and you are applying this to some h, you are looking literally at df1 ah, df2 ah, blah blah blah, dfk at ah. So we are saying, okay, we are saying that the derivative of f at a applied to h is just df1 at a applied to h up till dfk at a applied to h. And this is, okay, this is recovering what we know already about the vector functions, let's say, okay, gamma from r to r3, okay, where we say, okay, gamma, so gamma is equal to some gamma 1, gamma 2, gamma 3. These are the component, its component functions. So gamma prime of t, you would say, is gamma 1 prime of t, gamma 2 prime of t, gamma 3 prime of t, let's say. Okay, well, this statement is saying the same thing. The derivative of f is the derivative of each component function. It's the vector of derivatives of each component function. Okay, so that's is for the intuition. Okay, the proof we already did last time. So now we'll just move on to the next paragraph. Okay, now here in Cartan, page 33, after the theorem. Okay, so yeah, there's this note. So this note maybe I should give as well. Okay, the note is that, well, if you're looking at we know that f is continuous if and only if each fi is continuous. Okay, and that's something from let's say basic real analysis. Okay, what we did now was show that f is differentiable if and only if each fi is differentiable at a given point. Okay, at a, okay, and furthermore, f is of class C1, or if you want, f prime is continuous. So df is continuous at a, or f is of class C1, okay, at a. This is the same thing as saying that each dfi is continuous at a as well. Okay, so meaning that each fi, so i.e. each fi is of class C1 at the point A. Okay, at A. Let me note that when I'm saying f is a function is of class C1 at a point, what I'm meaning is that it's differentiable in the neighborhood, in a certain neighborhood of this point, and that its derivative in this neighborhood is continuous at the point. Okay, so yeah, as for this thing, okay, you just need to recall what we were saying about the, so sketch of proof, just sketch, because I'm not gonna do all the details. Okay, sketch. So let's say, okay, df is continuous at a. I want to prove that each dfi is continuous. Well, let's say, okay, so say first, let's do the backward implication. Okay, so say for all I, dfi is continuous at a. Okay, so let's remember that df at a, okay, is just the sum of uj around dfj, okay, at a, j equal 1 to k. Now note that this thing here, okay, this thing I'm writing here, this is not expressing the map uj around the map dfj applied to the point A. Rather, it's expressing the map uj composed with this map dfj at a, which is itself a linear map. Okay, so when I'm gonna be talking about this dfa, yes, I'm gonna be trying to prove that. So if I can prove, if I can show that for all j, the map uj around dfj at a is continuous, or let's say the map uj around dfj of dot is continuous at a, okay, then I conclude df is continuous at a. Why? Because df, okay, is just the map given by uj around dfj dot, okay, let's make an addition parenthesis, j equal 1 up to k. Okay, so let's call this map, so let me call L, okay, the map uj for a given j, uj composes dfj dot. Okay, so how does L look like? Well, L of a certain point x is just uj composed with dfj at x. Okay, so what's L doing? L is taking elements from, say, U, okay, where f is differentiable, okay, which is inside E, and it's going into the space of a certain space of linear maps, okay. Not going to specify the space now, but this thing is a linear map and this thing is a linear map, so it's going into an L of something. Both are linear continuous, of course, so a space of linear continuous maps of a sort, okay. Now, if I take a perturbation of A, so let's look at L of A plus H minus L of A. I want to prove that L is continuous at A, right? So this L, I want to prove it continuous at A. So I take a perturbation of A, and look at L of A plus H minus L of A. And known. Okay, let's try to prove that this thing tends to 0 as H goes to 0. Okay, so the norm of L of A plus H minus L of A, operator norm of course, okay, this is equal to the norm of Uj composed with dfj at A plus H minus Uj composed with dfj at A. Okay, and if I factor by Uj, in the sense of composition, this is Uj composed with dfj at A plus H minus dfj at A. Okay, operator norm. And I know that this thing is less than or equal to the norm of Uj, okay, times the norm of dfj at A plus H minus dfj at A, something we discussed earlier. Okay, now Uj is fixed, okay, and its operator norm is certainly bounded. It's some constant and positive for all our purposes. Okay, and might be 0, okay, it's a constant and positive. For the Uj is not going to be 0 because Uj is not the 0 map. Okay, and here, but we don't care. But here, okay, I have something which is actually going to 0. Why? Because, well, dfj is continuous at A, which means precisely that the limit of dfj A plus H minus dfj A, this thing equals 0 as H goes to 0. Okay, so this thing actually goes to 0, and then L certainly is continuous at the point A. Okay, and since each of the, so L was representing one of the Uj composed with dfj of dot. Okay, since each of these is continuous at A, then df, which is just the sum of these, okay, is itself continuous at A. Okay, now vice versa, you need to recall what each fj looks like, or if each dfj looks like in terms of df. So let's remember that df at A, okay, so df at A, okay, it's the sum from j equal 1 to k of uj composed with dfj at A. Okay, let's do this trick. So let's compose both sides by some pi. Okay, so fix I and do this. So pi composed with df at A is equals to pi composed with the sum of uj around dfj at A. Okay, j equal 1 to k. Now, since pi is a linear map, it's just, so we are saying pi composed with df at A is equal to the sum from j equal 1 to k of pi composed with uj composed with dfj at A. Now the thing is, pi composed with uj, okay, if I is different from j, this thing is just the 0 map. Why? Well, because pi is projecting the ith coordinate. If j is not equal to I, then uj is giving me something which is zeros except at the ith coordinate, okay, and j is somewhere else, say here, okay, then the pi is receiving the 0, okay, it's giving the 0. So pi composed with uj is 0 if I does not equal to j. But if I is equal to j, we know it's already the identity map, okay, if I is equal to j. So then I'm looking at pi composed with df at A being equal to what? So this sum disappears. Why? Because the only way for the pi composed with uj to be non-zero is for I to be equal to j. So I'm left only with the ith term. So I'm looking at pi composed with ui composed with dfi at A. Okay. Now this thing is the identity, so I'm literally saying that pi composed with df at A is the identity composed with dfi at A. So if you want, okay, df I of A, but it's just Pi around Bf at A. Okay, and then from here you can do a similar argument to what you did above to prove that, okay, Pi has the same desired properties as the Ui, and the df, okay, at A, or let's call it df of dot, okay, these two guys, when you compose them, you're gonna do the same argument as above to conclude that dfi must be continuous at A. Okay, you just write df at I, well, this is equal to Pi composed with df of dot, and you just replicate the argument you did above. Okay, so yeah, it's a fact that what you expect for a function landing inside a product space, okay, so f differentiable if and only if its components are differentiable, okay, and if f is differentiable, okay, then f is of class C1, or if you want, f is the derivative of f is continuous at a certain point if and only if the derivative of each component, okay, is continuous at this point. Okay, enough with this remark. Okay, let's now just in page 33 on Cartan, the example which is given next to this note, just after this note, talks about what we were talking about earlier, which is the special case where the product space is Rk for some k. Okay, so the Euclidean space. So we'll talk about what we usually understand by parametric curves, if you want, okay, or something like that. Okay, so you're talking about the special case that you know already, which we discussed earlier as the intuition for what we are doing here. Okay. Now, an application is given here, page 33. An application of this theorem about differentiability of a map and its relation to differentiability of its components when it's going into a product space. Particularly this application, okay, is talking about what we understand by the generalization of the product rule that we know in calculus in the which we took in high school. Okay, so I'm talking about this rule which says uv prime is equal to u prime v plus v prime u, or if you want, u prime v plus uv prime. Okay, now how to generalize this thing? First of all, here and generally we're not talking about products of functions, because we are considering functions which are landing inside vector spaces, non-vector spaces, and generally we cannot guarantee to have the notion of multiplication of functions or multiplication of vectors inside a general non-vector space. Okay, and the usual way to generalize multiplication is to consider a bilinear map. Okay, so if you remember when we talked about bilinear maps at the first time, okay, we gave this example of this map going from R2 to R, which is given by bxy equal to x times y. Obviously this is bilinear, okay, and this is the most basic bilinear thing in existence, okay. And bilinear maps, generally, they serve to generalize this notion of multiplication. Because a bilinear map, if you think about it, what's doing is that it's taking two stuff inside it, okay, it's giving you a certain expression, okay, which is expressing these two stuff in a certain form. But what's special about it is that when it's linear in the first and second argument. When you add two stuff for the first one, you're going to be able to distribute them, so to speak. B of x1 plus x2 y is the same as bx1 comma y plus bx2 comma y, which is the same as the distributivity property of multiplication. Okay, x1y plus x2y. And same story for scalars and linearity in the second argument. So really what bilinear maps are doing, they are trying to generalize what we understand by products of stuff. Okay, and that's the best thing we can hope to speak of when we are inside general non-vector spaces. Okay, so without further ado, okay, the application is the following. So I'm gonna just state it as a proposition. Okay, so proposition, so consider let f from E1 cross E2 into F, where E1, E2, and F are given non-vector spaces. Okay, let F be a bilinear and continuous map. So assuming that F is bilinear and continuous. Okay, now consider two maps. So consider U, okay, some open subset U of a certain non-vector space E into E1. Okay, so non-vector space is open, okay, and some V going from the same open set U living inside E into E2. okay, instead of E1. So suppose that both U and V are differentiable, okay, differentiable at a given point, say A, okay. So let's suppose U and V are differentiable at A, okay. Then the map which maps x to f of u of x, v of x, which is literally the map which is doing the product of u of x and v of x in our understanding, okay, is differentiable at A, okay, and its derivative, so let's call this map something, let's call it W, just as Cartan calls it, okay, and dW at a point A, okay, applied to H, is the same as f of du at A applied to H, comma, v of A, okay, plus f of u at u of A dv at A applied to H. So basically what's happening here, this is v prime, okay, this is u, this is u prime, this is v, and this is uv all prime. So we're saying uv all prime equals u prime v plus uv prime, thus recovering the thing which we have in calculus, okay, the product rule of functions, of differentiable functions. So this is the way it generalizes in general, okay, when you're talking about a bilinear map rather than a product, and you're considering u and v going into some non-vector space, okay. So how do we prove this thing? Proof is rather easy, okay. So proof, we're looking at the map W, okay, W which is equal to f of u dot v dot, right? So this is W of dot. Okay, so what's this map W? What are its true colors? Okay, what's it doing? We're looking basically at the composition, okay, of the bilinear map F with the map which sends x to u of x, v of x, right? If I call this map, let's say, what do we call it? Let's call it big H, or let's call it G, okay? We're not using G. So then w of x is just f of g of x, right? So w is in fact f composed with g. So if I can prove that G, this map G, is differentiable at A, okay, and I know that f is differentiable because f is a bilinear continuous map, okay. So if I can prove these two things, this thing I have for free because f is bilinear, differentiable at, I should say, not A, I should say u of A, v of A, okay, u of A, v of A. So again, I have this thing for free, regardless, because f is differentiable everywhere, okay, and this is what I'm missing. G is differentiable at A, okay. So how do you prove this thing? So G, okay, G of x is the map u of x, v of x. Okay, let's look closely to G. G is just a map going into, so from U subset E into the product space E1 cross E2, right? I mean, the U of x is landing inside E1 and the V of x is landing inside E2. So look at this function, which is of the type that we discussed earlier, which is the entire topic of our session here. Okay, this is a map going from a certain non-vector space E into a product, okay, of two non-vector spaces, and we saw that G is differentiable, okay, if and only if its component functions are differentiable, i.e., if and only if U and V are differentiable. Well, since U and V are differentiable at A by assumption, okay, well, this implies automatically that G is differentiable at A. Okay, but furthermore, let's compute. Now, of course, G is differentiable at A, so we have this thing now. Okay, and we have that F is differentiable at U of A, V of A. So conclude the map W. Okay, the map W, which is F round G, So therefore, W, which is f round G, is differentiable at A. Okay. What remains now is just compute the derivative of W. So dW at A, okay, by the chain rule, this is just D. So this is D of f around G at A. By the chain rule, this is dF at G of A, okay, composed with dG at A, right? And let's insert some H here just to make computation easier, okay? So dW at A applied to H, this is dF at G of A applied to dGA at H. Okay, now what's G? Again, G is the map U of X, V of X. And by the very theorem that that's the topic of our work today, okay, dG at A H is just du at A H, dV at A H, right? And well, the F is a bilinear map. And we know that a bilinear map has a special derivative. If a map B is bilinear, then dB at xy hk is just B of hy plus B of xk. Okay. So now dW at AH, so dW AH, which is dF again at G of A, okay, applied to dG at A H, well, write this explicit. This is dF at, what's G of A? Well, it's U of A, V of A, and what is dG at H? dG at AH, this is just this thing here. This is du at AH, comma, dV at AH, okay? And, well, by the formula of a bilinear derivative, okay, derivative of a bilinear map, this is just f of du at AH, comma, V of A, plus f of, well, U of A, dV at AH, which is exactly the thing we wanted to prove. Okay, so U prime V plus U V prime. Okay, so this finishes the proof of this proposition. And yet another more particular application, special case of this one that we just talked about here, this proposition, is when you are in a Banach algebra. So we're talking about the product rule, right? And we're trying to generalize this product rule. And we're saying, okay, you not necessarily have the ability to multiply U and V. If you are taking U of X, okay, and V of X, there needn't be something like the multiplication of U of X and V of X. And that's why we require it to be talking about some continuous bilinear map F, which is connecting U to V in this manner which we desire. Okay, but remember that when we're in an algebra, we have multiplication. An algebra is defined by the multiplication. So as a reminder, okay, it's something we talked about before, just as a quick reminder. So an algebra, okay, an algebra is some A with a addition, some scalar multiplication, and a product of vectors. Okay, so scalar action, okay, and the thing here, the multiplication of vectors. So it is a vector space, okay, it's part of it is a vector space, okay, and this additional part here allows you to multiply vectors by each other. Okay, so multiplication of vectors living inside A. Okay, that's an algebra. It's a vector space with a product structure of vectors. A Banach algebra, okay, the other hand, well, it's a specific kind of an algebra. It's an algebra, okay, first of all, okay, which is equipped with a norm, has a norm. This norm, so let's specify these as part of this sub-branch. Okay, so has a norm such that for this norm it's Banach, it's a Banach space. Okay, and such that if you take any U and V, or let's just call them A and B. Okay, if you take A and B inside A, then it's necessarily true that the norm of A times B is less than or equal to the norm of A times the norm of B. we require this kind of thing, okay? And basically that's a Banach algebra. Now, when we are in an algebra, we can multiply stuff, right? And the thing is, that's what we're after, multiplying. So we are after the map u of x times v of x in a sort. That's what we are after in the proposition we talked about above. So here we have this for free, because if you define u to be from some open subset u of e in all vector space into a Banach algebra, okay, let's just say an algebra for now, and you'll see why it needs to be a Banach algebra in a bit, okay, and some v from u, the same u, into the same algebra, okay, and if you consider the map which associates x to u of x times v of x, this is a genuine, well-defined map, because u of x is an element of a and v of x is an element of a, and it makes sense to say u of x times v of x. So here for us, f, the map which we were talking about above in the proposition, which is bilinear and continuous, this map is for us here the product of two elements of the algebra A. Okay, it's the map. So f is the map taking x, y inside A squared to x times y. Okay. Now, the thing is, this map here would not be continuous. It's a bilinear map, of course, but it would not be continuous had A not been a Banach algebra. Okay, or at least does not need to be a Banach space, but it needs to satisfy this property here. Okay, because this property is what allows this multiplication here, this multiplication map f, to be a continuous bilinear map. Okay, so so f is continuous bilinear, and if you assume that u and v are differentiable at some point a, okay, so u and v say differentiable at a in u, okay, then I can apply the above proposition, okay, to say that the derivative, okay, of the map w, which we defined as w of x being f of u of x v of x, which for us here is just u of x times v of x, okay, derivative of w at x or at a, okay, applied to h, is just f of du at a h v of a plus f of u of a dv at a h. Now f is just multiplication, right? So dw at a applied to h is just du at a h multiplied by v of a plus u of a multiplied by dv at a h, which is yet a more a closer form of the product rule. Okay, so we're literally saying here uv prime at a thing. Okay, so forget about the h, it's just artificial, just there to make it clear that you are inserting the h here. Okay, so you're saying really uv prime at a is just u prime at a v of a plus u at a v prime at a, okay, so to speak. So this is a more particular way to see this thing we are talking about. So that's for the regarding landing inside the product spaces. Now the next section in Cartan 2.6 is about when your domain is a product space. Okay, and that's gonna take more work than what we did for landing inside product spaces. We're gonna be talking about partial derivatives, gradients, stuff like that. And I want to talk about the intuition for partial derivatives and this stuff. I'm gonna postpone talking about your domain being a product space. I'm gonna postpone it till session number 12, okay, or 13, depends on how much time we'll spend on exercises and problem solving, which is gonna be the next session. Okay, but for now, in the remainder of our time today, let's just talk about the particular case when we are considering, instead of R differentiability, C differentiability. Cartan talks about this, okay, in section 2.8. So this is section 2.8. And I'd say half of this is something that you should know, and the other half is just some culture, okay, about holomorphic maps. So the thing is, when we started out this course in the introduction, we were saying, okay, it doesn't matter if your field over the vector space over which the vector space is defined, okay, is the reals or the complex numbers. For the purposes of the general theory, okay, so the vector space is naturally something which is equipped with a plus, making it an abelian group, and a scalar multiplication coming from the field, so field scalar multiplication, coming from the field over which it's defined. There's no such thing as a vector space by itself, okay? There's a vector space over a certain field, where this field is what provides scalar multiplication. And of course it matters which field you are working over for all kinds of purposes. Like for example, when you're talking about the dimensions, okay, the dimension of a vector space, say R, or let's say C2, okay, dimension of the space C2 as a C vector space, this is 2. But the dimension of the vector space C2 as an R vector space, well, this is 4. It matters, okay, different dimension. And it matters in terms of course, bases, which are what are providing the dimensions, okay, matters for many considerations. But for the general theory we're doing here, like for example the chain rule, okay, or the things we did previously, okay, all sorts of stuff we did so far, there's no place at which we say, okay, we needed the scalar lambda which we are multiplying a certain vector by to be real. Okay, we never needed lambda to be real, so to speak, okay. This was never an explicit assumption, so therefore lambda could have been complex as well, okay. The general theory we are doing does not matter which field you are working over, but the thing is, when you are considering differentiability over a C vector space, and this term I maybe should make more clear, okay, C vector space, what does this mean? Simply means, so when I say a C vector space, it means a vector space, okay, with C as scalars, okay, or if you want, a vector space over the field C, okay. And when I say an R vector space, okay, I'm meaning a vector space over the field of the real numbers R, okay, so with R as scalars. And for the general theory, it does not matter if you are working in C or over C or over R, but for the properties of the functions you are dealing with, okay, it does matter a bit, okay, because when you're doing analysis over the field C, when you're considering functions which are differentiable of the field C, they have peculiar properties, okay, which are very rigid, what are known as the Cauchy-Riemann equations, okay. And they are coming from this very fact that the linear map, so recall, a function f, which is defined on an open subset U of a certain non-vector space going into some non-vector space f, okay, is differentiable at a point A, okay, if there exists some df of A, which is going to be a unique linear continuous map, okay, from E to F, so df of A belonging to the space L of EF. But the thing here is that it matters if you say, okay, f is R differentiable, or if you say f is C differentiable. Not for the correctness or incorrectness of the theorems we did so far, everything we did so far, but it matters for how you understand the function f, okay. So to be more clear, R differentiable means that df of A, this thing we are talking about here, is an R linear map, okay. And f is C differentiable means that df of A is C linear map, okay. Now by default, if f, same situation, okay, f is C differentiable, well then df of A, C differentiable at A, df of A is C linear, okay, and then df of A is R linear, well, because every C linear map is also R linear, so df is necessarily R linear, and f is real differentiable, f is R differentiable, okay. So every C differentiable map is real differentiable. This thing here, okay, why is it correct? This implication. If we have a linear map L, okay, which satisfies that L of lambda V equals lambda L of V for all lambda in C and for all V in your vector space, okay, then if I say, okay, L of some mu V, okay, where mu is a real number, okay, well, this is also mu times L of V, because being a real number implies that you are a complex number as well, because R is a subset of C. Every real number is by default a complex number. So if a map is C linear, then it is necessarily R linear. Okay, and when we say something is C differentiable, we can say directly that it's also R differentiable. Okay, but the converse, of course, is not correct. Okay, so if you are R differentiable, okay, this does not imply that you are C differentiable, at least not always. Okay, so, and the reason for that is that, well, the space of bounded linear maps, when you say df of A, okay, belongs to L of EF, we're saying bounded linear maps from E to F. But linear in which sense? R linear or C linear? To be precise, we have to say, okay, well, it belongs to LR of EF, so a linear map from E to F as an R linear map, versus, and continuous of course, versus saying LC of EF, a C linear map from E to F, which is continuous as well. Okay, these two spaces are different from each other. They're not the same space. Okay, but it's a fact that LC of EF is a subspace of LR of EF, because every C linear map which is continuous is also an R linear map which is continuous. Okay, but it's not a it's a proper subspace. Okay, and for maps which are C differentiable, we said very briefly the Cauchy-Riemann conditions. These Cauchy-Riemann conditions, they are coming from this very kind of thing. Okay? To be more precise, this along with a few other stuff, but this primarily was causing the additional constraints to come into existence. You talk generally about a map F, let's say going from C to C for simplicity. Okay, say F is differentiable. Okay, you write F, so F is F of Z, right? Taking complex number, and the complex number can be identified with a real couple x, y, and say, okay, this is U plus IV, where U is a function of x and y, and V is a function of x and y, and both U and V are landing inside R. Okay, so the function is going to R. So if F is differentiable, you realize that U and V, they satisfy a certain PDE. Okay, there's a certain relation between Ux, derivative of U with respect to x, and the derivative of V with respect to y, so del V by del y. Okay, these things are actually equal, and Uy is equal to minus Vx. It's the other relation that is satisfied. These two relations are called the Cauchy-Riemann equations for a function which is differentiable as a map from C to C as a C. So we're looking at these as C vector spaces. Okay, and these additional constraints on such a function create a whole new theory. Okay, the entire theory, which is the complex analysis. Okay, and this should be emphasized that what we are doing here in this course, although as a general theory, okay, it includes what you can say about C differentiable maps, but it does not treat complex analysis in any kind of way, not even a light way. Okay, does not treat complex analysis at all. Okay, so complex analysis is an entirely separate thing than the thing we are doing here. Okay, I felt this thing should be noted. Okay, it's already talked about in Cartan, and it should be noted because it shouldn't be understood that whatever we are doing here just applies randomly everywhere. Okay, in the sense that there's nothing else to expect. In complex analysis, there's much more to expect. The entire theory lies behind this very nuance, okay, of being a C vector space versus being an R vector space. Okay, so that's for today. And next session is going to be a problem-solving session. And I think it's very probable that we're going to do problem-solving, exercise solving upon in sessions 11 and 12, both these sessions, because we have a lot of exercise to solve. If you remember the last exercise session, the first exercise session, basically, by then we still haven't done anything regarding differentiability. We barely talked a bit about differentiability, and I quickly remarked what it means for something to be differentiable when it lands inside a non-vector space. but we still haven't. By then we still haven't done anything regarding differentiability when your domain is a non-vector space, and you haven't done the chain rule. So there are some stuff which we have done now that allow us to solve many more exercises, and I feel they are very needed at this point, just to give this material some context. So we're going to be doing various exercises, okay? Applying the chain rule many times just to emphasize why it's important. We're going to be doing some infinite dimensional vector spaces. We're going to be seeing different types of linear maps, different types of possibilities for vector spaces, for a variety of what you can do with this theory of differentiation on non-vector spaces, which is the entire, purpose of this course. Otherwise, this would have been just analysis on Rn, say, on a finite dimensional vector space. But the thing is, since we are working on general non-vector spaces, the possibilities are much more, and the intricacies are much more as well, as we will see in the exercise sessions. So, I'll thank you for watching today, and I'll see you next time. Okay.